When we were first introduced to antiderivatives back in section 4.9, we talked about how a couple of the derivative rules gave us some nice relationships with the antiderivatives. In particular, we still have constant multiplication rules for antiderivatives and some rules for antiderivatives, but we also saw that working with the product rule was just going to be too messy and difficult to deal with. We didn't even bother trying to take a look at the quotient rule because that's even harder. But we mentioned that the chain rule is something that we were going to come back and try to work backwards after we had a little bit more practice. Now is when we're doing that. And so the main focus here is really on using substitution on antiderivatives. But now that we've talked about the fundamental theorem of calculus, we should realize that if we're trying to find definite integrals, which is nothing more, again, than the notation that we use for net area, but if we're looking to evaluate, excuse me, the net area of the definite integral, we're using antiderivatives as well. And so that's why it shows up here in section 5.5 much later. So just a quick reminder, all we really did last time when we were talking about the antiderivatives and the chain rule was just mention that if we're taking the derivative of something to create a rule here, we're going to want to take the derivative of some antiderivative, that way they cancel each other out. So we're just taking a look at the derivative of the antiderivative of f evaluated at g of x. And so just another reminder here, this represents the antiderivative because it's a capital letter. This is just a regular, whatever function it happens to be. And the chain rule tells you to take the derivative of the outside, evaluated at the initial inner function, but then we also have to multiply it times the derivative of the inner function. And then we immediately said, I'm not even going to draw another line here, we immediately said the derivative of the antiderivative, by definition, is just the original function f. Okay. And then finally, we just can, from here, take the antiderivative of both sides. And remember that the antiderivative and the derivative are opposites, so these are just going to cancel out. And down below, there is nothing to cancel. So what we're left with is putting this together is that the antiderivative of the function f evaluated at g of x times g prime of x is equal to the antiderivative of f evaluated at g of x. And the one thing I didn't bother to write up above is remember that if we're working with a straight antiderivative, we have to worry about the plus c. If we're working with a definite integral, that plus c is just incorporated as part of the problem. Okay, so I kind of cheated and did a run-on sentence, run-on equation, whatever you want to say, but this is really the reverse of the chain rule that we're going to call working with substitution. Okay, so the key thing here is that we need to still, just like the chain rule, we need to identify what the inner function is. And once we identify what that inner function is, we need to make sure that the derivative of the inner function is also part of our problem. Okay, so initially here, I have to make sure it's absolutely clear. The first, about half, maybe the first half of Calculus 2 is learning all about all sorts of different integration rules and how you can handle different situations. So to be clear, working with antiderivatives and working with definite integrals is one of the harder things to do in calculus. This is not going to work in every sort of instance. Now, you're not going to always have some sort of function where it's complicated, but hey, that inner function also has a derivative that's sitting on the outside. So be aware that there's plenty of integrals out there that you're not able to calculate right now. This is just our first step into dealing with some things that are a little bit more complicated. All right, so if I need to, I can redo this video and give you an actual checklist to write down. So let me know if that would be helpful. But I think this idea is really much easier to talk through just by doing examples. So maybe at the end, if this video hasn't gone too long, I'll kind of give a sketch as far as the, this step first, the next step, so on and so forth. But the main idea is just to try to recognize the pattern that's happening. And so we have to have an outer function, an inner function, and the derivative of the inner function to be able to use this. And notice that when we take the antiderivative, all that really happens is we take the antiderivative of the outer function, and the inner function just kind of stays put, and that derivative disappears. Okay, so that's how we can kind of think about it if you want to try to mentally do this. But without a bunch of practice, that mental sort of idea is a little bit tricky, which is why we use something called substitution. Okay, so let's just leave this here, erase some of the stuff up above that we don't need anymore, and very much like you use substitution in an algebra class, especially when you're maybe factoring to make it look a little bit easier to deal with. Instead of working with a couple of functions here, let's just look in terms of replacing the function with what appears to be a variable. It's not really a variable, it's just going to look like a variable so that it's a little bit easier to handle. But we're just going to say, hey, let's let u represent whatever that inner function is. Okay. And then from here, excuse me, we're going to have to talk a little bit about what this guy means again. And so I don't want to make a huge deal about this, but when you go back through it and look at maybe previous videos or notes or whatnot, remember that that was called the differential. Okay, the differential is just a small change, in this case, in x, that typically relates to the tangent line instead of the function itself. But the quick idea here, there's a little bit more going on here than necessary, but the reason we use this notation is if you think back to our Riemann sums, we got the height of our rectangle from our function value. So this is a crazy function that has some inner changeability here. But this whole thing would be giving you the height of the rectangles in a Riemann sum. That's the width, right? dx is very close to the same thing as change of x. And so what this is really saying is to sum up, remember that's kind of a squiggly s, so sum up all of the areas when you multiply the height of the rectangle times the width of the rectangle. Okay. But at the same time, if you remember earlier in chapter 4, we talked about this as kind of a whole expression. Okay. Remember, we had a setup that just kind of said, if I have some variable equal to a function, then when I take the differential or find the differential of that variable, that is always equal to the derivative of this function times the differential of x. Okay, so I don't want to overdwell on this because a lot of students just kind of look at this and say, well, that's just a nice easy pattern. If I just kind of pretend that d stands for derivative, I'm just taking the derivative of u to get du, the derivative of g gives me g prime of x, and we have that dx here as kind of the derivative of the inner function if you're thinking about the chain rule. It's technically not that that's going on. This is a differential in section 4.6. You need to go look at that section again to make a little bit more sense of this, but that's the relationship that we're coming up with. Okay, so if we make this substitution, then this integral looks a lot easier to deal with. Okay, so let's just go ahead and get rid of the extra stuff and make the substitution that we just wrote on the board. G of x is being replaced by u. That's the very first substitution that we made. So that would become a u. And then look how nice this works out. Right? We have this g prime times d of x. That's exactly what happens when we think about the differentials with our variable that we're substituting with. This g prime of x times d of x is exactly the differential in u. Okay, so this just becomes the antiderivative of some function with respect to u because of the du here. And likewise, there's not nearly as much to worry about over here, but the g of x gets replaced with the u over there as well. Okay, so the moral of the story here is that we do this as kind of a first step to go from working with the crazy looking expression that's a little bit tricky to work with to something that, as long as we're working with a function that we're comfortable with, that we've learned about, we can certainly take the antiderivative of that function and evaluate it at whatever u happens to be. And again, at this point, we would just go ahead and replace the u with the g of x and kind of do our back substitution and figure out the exact expression. Okay, so that's the basic idea of substitution. And we'll have to talk about a little bit more of a detail when we get into working with the definite integral as opposed to just a generic antiderivative, but we'll hit that when we get to that example. Okay, so our first example here, let's say that we're working with the antiderivative of 8x times cosine of 4x squared plus 3 times dx. Okay. So again, maybe before you do anything else, just take a quick glance and see if it makes sense to try to take the antiderivative of what is written up here. But as we've talked about, we've never talked about an antiderivative of a product because that was too difficult. And if this was just an 8, then maybe we can talk about trying other ways. But because there's an x here and an x there, that would be the product rule. There's no working backwards from that. And so as soon as we see that it's too complicated, we come through here and pick out what is the inner function. And as long as you're comfortable with the chain rule, it's the same idea as always. So I'm going to be a little bit silly and say, well, you can choose between the 8x, the cosine, or the 4x squared plus 3. But if you're choosing the inner function, it's whatever function is inside of another one. So this is certainly the inner function. So we're going to make the substitution that u is equal to 4x squared plus 3. And du then would be the derivative of this expression. So the derivative of 4x squared is 8x. The derivative of 3 disappears because it's a constant, and we still have that dx. Okay. So as a heads up, this won't always happen this nicely. This was just our first example. But what we noticed then is that we have the 8x dx here matching up exactly that we need. And so that is where this would fall apart. I don't want to completely change the problem, but just like I do in class, I just want to make sure that this is clear. If that would have been, say, an x to the 4th out here instead of just an x, now this doesn't match. This 8x to the 4th up here doesn't exactly match the derivative that we had below. There's no way that we're going to make this substitution work out in a nice manner. And so that's why we have to be careful. We just kind of run with it at the beginning and just kind of hope that the textbook or your teacher is not trying to trick you. In this sort of circumstance, we're not. This is kind of the introduction. We're not trying to trick you into doing things that you're not going to be able to do. But you have to check. Once you take the derivative, double check. Does that x, don't worry about the coefficient, because remember, we can always deal with constant coefficients in different ways. So we don't really care about the 8, but let's just make sure that we have an x here to match up with the x that is also showing up above. Okay. So anyway, this does work out. So we can take a look at putting this together. I don't want to have to rewrite it, but at 8x times dx, that is absolutely equal to du. And again, we're just replacing 4x squared plus 3 with u. So doing all of that, the 8x, the dx is gone. It's replaced just with that du that we typically write at the end. We haven't done anything to cosine, so it's still a cosine. And that 4x squared plus 3 is being replaced with a u. And so again, we went from a relatively scary looking problem to one that if you have your antiderivatives memorized, this is a piece of cake. The antiderivative of cosine is sine. We're still taking sine of the same variable expression, whatever here. Since this is just an antiderivative, we don't have any definite integral going on. We still have to have the plus c. And then the very last step, of course, is stepping back and saying, well, hey, the initial problem had a whole bunch of x's. It doesn't make sense for my answer just to have a u in here. So replace the u with the original expression, kind of our back substitution. So that u was equal to 4x squared plus 3. So replace that, and we're finished. And you can always check your answer using derivatives, and I would absolutely encourage you to do that. So I'll try to talk through it without writing it all out, but if we took the derivative of this, we should be getting the original function that we had here. So the derivative of sine is cosine. You're taking cosine of the same function that we started with here, so that's good. But then you also need, by the chain rule, need to multiply by the derivative of the inner function, which is exactly that 8x. And of course, the derivative constant just disappears. Okay. So that's what the substitution method looks like if everything works really, really nicely. And there are going to be some times where we have to make a little bit of adjustments here with our constants, but other than that, this is the typical setup. All right, so let's move on to a definite integral instead of just a random antiderivative to make sure that we don't go too far before we tack on the one remaining idea. And I dropped my notes, apologize. So let's say this time we had the definite integral going from 0 to 2 of x squared times e to the x cubed dx. Okay, so obviously the huge difference here is that we have numbers indicating that this is a net area definite integral, not just an antiderivative. Okay, so the key thing that you need to be aware of here is nothing more than when we write the 0 and the 2 here, these represent values that we're eventually plugging into, in this case, x, since that's the variable we're using. So you don't actually have to write these up here if you don't want to, but mentally, you should be aware that we're finding the net area under this curve between x equals 0 and x equals 2. So the only reason we have to be careful with that is that if I am changing variables, I'm going to be changing the inner function, I'm going to be changing the dx, I also have to change these variables. It's not going to do me any good to change all of this into the u's if I leave these as x's. Okay, so that's the only extra step that we have to be aware of here. So once again, your u should be representing your inside function. So your choice here is x squared e or x cubed. Of course, x cubed is inside the exponent for e, so that is the substitution that we want to make. And then we use our differentials. Again, I'm going to kind of cheat and say take the derivative of both sides. That's not really what's happening, but it's what it looks like is happening. So we get du is equal to 3x squared dx. Okay. And you can see here that we're going to have to mess around with a little bit of a constant because we don't have exactly the 3x squared up here, but we at least have the x squared. It's not going to be a huge deal. So let's actually talk about taking care of that first. There's a handful of different ways that you can do this, but what most students end up doing, especially if you have just kind of a blank up here, is just saying, well, I need there to be a 3 here, so I'm going to write a 3. But of course, I can't just write a 3 that changes the problem. I have to counterbalance it. But remember, we have our constant multiplication rule here. Okay, so let me take a step back here. I'll put that 3 right back, but I just want to make sure it's clear. If we started with the number in front of, and as a coefficient in front of the x squared at the beginning of the problem, we could pull it out here. Or vice versa. If there was a coefficient multiplying times the net area, we can multiply it and bring it inside. That's one of our rules for working with antiderivatives and definite integrals. So the idea is that multiplying on the outside, multiplying on the inside, they have the same effect. It doesn't matter where you put it. So I needed to talk through that to make sure it's clear that if I'm going to multiply by a 3 here, I need to counterbalance it by multiplying something out here that would cancel it out. So there's no equation here. This is not saying I'm multiplying by 3 on both sides of the integral. That's not an equal sign. But if I need to cancel that 3 out, I need to multiply by the reciprocal. And so to a degree, it's a little bit like the antiderivative rules we had for the e or the trig functions, where if there's that extra coefficient, we had to cancel it out by multiplying by the reciprocal. The same thing's happening here. If you need to put in this 3 to make it match up with our substitution, just throw it in there, and then just multiply by the reciprocal outside of that integral so that we can counterbalance the effect that we just had. Okay, so at this point, we have the x cubed going on. That's perfect. We have the 3x squared dx that we've taken care of. The only thing we have left that we have to deal with are these x is equal to and x equals 0. Okay, so all we have to do, and we don't have to write it out in words ever again, but all we have to do is realize that when x is equal to 0, then u would be equal to, remember, u is equal to x cubed, so u would be equal to 0 cubed, which is still 0. And likewise, when x is equal to 2, then u is going to be 2 cubed, which would be 8. Okay, so putting it all together, we've got the 1/3 on the outside now. The limits of the integral are not 0 and 2 anymore. Now it's 0 and 8. And then, just to double check here, the 3x squared and the dx match up with the du. So those disappeared, so we can just write a du in our integral. The e is our outer function. It's going to stay exactly as is. And the x cubed gets replaced with u. And so again, there's quite a bit of kind of thought process to get the substitution in there. But once you get used to this sort of pattern and how you write it out, the antiderivative, this very last step, that's supposed to be the easy part. And so here, the 1/3 is just going to stay. And then the antiderivative of e is, of course, itself. And remember, with the definite integral, we don't worry about the plus c, but remember our fundamental theorem of calculus tells us that we have to evaluate this expression at 8 and at 0, and then subtract them. Okay. So at the end of the day, this is not a hugely complicated expression. I guess I can fit it if I keep going. So I'm going to end up with 1/3 e to the 8 if I evaluated 8 first, and then I'm subtracting away the same expression evaluated at 0. Okay, but keep in mind, I just left this because e to the 8th, who knows what that is without a calculator, but anything raised to the 0th power is just 1. So 1 times 1/3 would be 1/3. Okay, so if you're looking for an exact answer, and be aware, sometimes MyMathLab is asking for an exact statement like this. Other times it's going to tell you to round to 3 decimal places, so pay attention to what it's asking you for. But this is the exact area under the curve of this function between x equals 0 and x equals 2. And so the other idea here is just to be aware that because we're actually plugging numbers in and calculating, there's no back substitution like there was with antiderivatives. We already have u. This whole problem is converted. There's no reason to go back and try to do anything with the back substitution. And so if anybody's curious, if you actually put this in your calculator, run through the calculation, you should end up with about 993.32 square units, if you want to call it that, but we don't need to have it here. All right. So if you can kind of get through these first 2 examples, then you've got all the tools you need to do any of the rest of the problems. Okay, so we're going to do 2 more of each type. I'll try to speed up a little bit. And we're just doing a variety of different functions here to get you used to the way things might look. So this one, let's do another definite integral. Let's say this one, we're going from 4 to 9, and we have a crazier looking expression. So here, maybe the square root of x plus 1 raised to the 4th power. And in the denominator, we have a 2 times the square root of x. And we're still working with the dx over here. Okay. So once again, our first step is to identify what the inner function is. And so I want to give you a heads up, and we'll actually kind of talk about this in another example. If you're working with a fraction, anything that's part of a fraction is kind of an inner function. You could call 2 times the square root of x an inner function because it's inside this fraction. Likewise, you can say the whole expression up here raised to the 4th power is an inner function because it's inside of the fraction. But in general, if you have that extra set of parentheses, that's almost always what you want to choose for your inner function. But to give you a little bit of extra information here, if you are having to choose between which one is which, whether it should be the numerator that's the inner function or the denominator that's the inner function, just check. If I take the derivative of the denominator, for example, do I get something that looks similar to what I have up in the numerator up there? And no, there's no way you're going to end up taking the derivative of this and end up with a plus 1. It's just not part of our rules for taking the derivatives of a square root. But if I take the derivative of the square root of x plus 1, the derivative of the square root of x is 1 over 2 times the square root of x. The derivative of 1 would just disappear. And so this is going to, kind of thinking ahead, it's going to give us the derivative that we need. Right? So I guess what I'm just saying is if you have a gut instinct in terms of what the inner function should be, just do it. You're probably right. But if you're uncertain, just try to think a step ahead. And even if you don't feel comfortable thinking about it, just pick one. The worst thing that can happen is you pick u is equal to the wrong one. You take the derivative and say, whoa, wait a second. That doesn't look like it shows up anywhere else. And then you just kind of recover from that. And so in this one, though, again, just kind of stepping back, because we have the set of parentheses, that's screaming out at us, let's make u equal to the square root of x plus 1. So I make sure that plus 1's outside of the square root symbol. And so now, again, there's various ways you can take the derivative of the square root. I've mentioned in past videos, or even in past videos, that you should probably memorize this one, but you can write it to the 1/2 power, do that sort of thing if you want. But the derivative of the square root of x is 1 over 2 times the square root of x. The derivative of 1 disappears, and we still have our dx. And so again, you should really be smiling here, right? We know that this 1 over 2 square root of x. I guess maybe I should put the 1 over here to make sure it's clear. This is 1 over 2 square root of x, just like it shows here. But that 2 square root of x dx is going to get replaced with du. And the square root of x plus 1 here is just your u. Okay, so all we're left with here is the integral from, well, let's talk about where it comes from in just a second, but kind of doing the substitution first. All we have left is a u to the 4th. Be careful that you don't go too fast. That 4th power is still out there, so we have a u to the 4th power du. So once again, in our substitution, the 1 over 2 square root of x matched up with something we had, so we just replaced that whole thing with du. The square root of x plus 1 got replaced with u. We still have the 4th power. And then finally, just make sure that we change our endpoints. Remember, these are x values. We can't keep x values if everything else is u. So just a different notation that you can use here. You don't have to, but remember, u is really kind of a function. So if we want to write it out faster, we can say u, when x is equal to 4, would be kind of like evaluating the function at 4. So I throw the 4 in here. Square root of 4 is 2. 2 plus 1 is 3. And if I evaluate the u at x equals 9, square root of 9 is 3. 3 plus 1 is just 4. So the limits of the integration here are 3 and 4. You know, that was the lower, that was the upper. So that's what we have. Okay. Now everything is once again relatively straightforward antiderivative. Okay. So again, really as you're looking over these videos or practicing, this is what you should be focusing on. And then just verify that you're not making mistakes with the antiderivatives, but you've had a decent amount of practice with those already. So the antiderivative of u to the 4th tells you to raise the exponent by 1, multiply by the reciprocal of what you just wrote, and then we have to evaluate that at 4 and 3 and do our subtraction. Okay. And so here, when you plug this in, I guess I'll make sure it's clear. You're plugging in 4 into u, so we're going to get 1/5 times 4 to the 5th power minus 1/5 times 3 to the 5th power. And don't try anything fancy here. And there's no way to kind of do the subtraction now. You have to go through and do your evaluation. But 4 to the 5th power using a calculator ends up being 1,024. And multiplying that times 1/5 is just going to put it over 5. And 3 to the 5th power ends up being 243. Okay. So I'm only writing that out because every once in a while students try to get going too fast and look at this and say, well, 4 minus 3 is 1 and everything else is the same, so I'm just going to get 1/5. You actually have to be careful that you're doing the arithmetic there. If you do the subtraction, if you want to leave it in a fraction, you're going to get 781 over 5. But you can divide that out and get an exact answer in terms of a decimal would be 156.2. So once again, just in your homework in my math lab, pay attention to what it's asking or what format of the answer it's asking for. Okay, so there's that example. Right, so let's go back and do another one where it's an antiderivative instead of a definite integral, just to make sure we go back and forth here and realize there's kind of two separate types of problems. So this go around, let's say we're working with the antiderivative of x to the 9th times sine of x to the 10th dx. Okay. So we're back to one that's a little bit more obvious, and we have a function inside of another function. So your value u is going to be x to the 10th. When you take the derivative to find the differential, you end up with a 10x to the 9th. And once again, this one doesn't quite match, but it doesn't take much to change. Right? We have the x to the 9th that we want along with our dx. And of course, we made the substitution so that the x to the 10th is taken care of. So we just have to make sure that there's a 10 out here. If I put a 10 out here, I have to multiply by the reciprocal on the outside. And now we're back to being home free. 10x to the 9th dx, that together becomes du. And of course, x to the 10th is just u. So what we're left with is the 1/10. We still have our integral. Sine did not change, but we're working with sine of u. And all this stuff became the du. Okay. So if this is seeming like it's getting easier, it's not really. Maybe this was a little bit less scary of an expression than the one we just did. But if it seems easier, it's probably because you're starting to get used to it, which is a good thing. But make sure you don't get overconfident either. I know sometimes I do that. So finally, Again, we're just working with an antiderivative, so we don't have to worry about the limits of integration here. We just take the antiderivative. Be careful with this one. It's really easy to misremember, but the antiderivative of sine is actually negative cosine. Okay. And then, of course, now that we have an antiderivative, we have to have the plus c because we don't have the limits of integration telling us kind of what the constant ends up needing to be. And then finally, I would not leave it in that format at all. I just take this one step further. Positive times a negative is a negative. We have a 1/10 in front of the cosine. And then also, don't forget, we can't just leave a u here. We have to replace the u with whatever expression x we started with. So that's going to be a cosine x to the 10th, and then we have that plus c. And so maybe I should have mentioned this with the other two after we took the antiderivative. But again, you can always check using the derivative. And the two definite integrals, I didn't do that because our final answer was just a number. But in kind of a halfway point, if you wanted to, you could have checked that antiderivative that we did in the middle just by taking the derivative. But if I did that here very quickly, the derivative of cosine is negative sine. So the two negatives would turn positive. We just get the sign here. We'd still be taking sine of x to the 10th. And then I'd have to, by the chain rule, multiply by the derivative of x to the 10th to get the 10x to the 9th that's out here that, again, gets canceled out by the 1/10. And so everything's good here. All right, so let's do another, actually two more kind of trig problems, because trig tends to be the ones that mess students up just a little bit more. So in that first problem that we just did, we had an exponent on, the variable itself. What if you ran into something like the antiderivative of maybe 3 cosine squared of x times sine of x dx? And I guess I probably didn't need a parenthesis around that cosine. I just wanted to make sure it's clear that that square is on the cosine. It's not on the x. Let me just get rid of it because that's not usually how you'll see it. And maybe I'll put a dot there just to make sure that we're clear about that. Okay. So if you look at a problem like this, it kind of feels like there is no inner function, right? It looks like we're taking cosine of x, sine of x. There's no reason to make a substitution. Let's make u is equal to x. So this is where you have to be very careful that you pay attention to what that square means. That's something we've definitely dwelled on previously in the class. So you don't have to rewrite it, but if it helps you remember that cosine squared literally means take cosine of x first and then square it. And if you write it like that, I think it becomes blatantly obvious what our inner function has to be. There's a set of parentheses. Our inner function has to be what's inside the parentheses. So we're back to using u is equal to cosine of x. So again, compare and contrast here. This time the whole trig function is our inner function, whereas the last example, that x to the 10th, or the variable raised to an exponent, that was the inner function. So this is a similar problem, but different in the way it ends up at the end. So the inner function, again, is cosine. Take derivatives to find the differentials. That du would end up being negative sine of x dx. And once again here, we are in pretty good shape. We made the substitution so that cosine of x is going to become a u. That's good for us. And we have the sine x that we need here, but we've got an extra 3 and we need a negative sign. Okay, so this is, again, where you can just play around with your constants. All right, so there's a couple different ways to play around here, but what I would tend to say is let's just first move this 3 to the outside of our integral symbol so that's not in our way. Okay, that's just our constant multiplication rule for antiderivatives. So we'll just move that out, and I'm just going to erase it. Let's just cross it out. And then finally, that gets rid of the 3 that was on our way. So now we have just the sine x, but we need a negative sine x. Okay, so I could put the negative sign clear in front if it would be a little bit easier to visualize, but I'm going to put it right in front of the sign to make sure it's clear that we need this to be a negative sign. Well, if I multiply a positive times a negative, it makes the whole expression negative. And then once this whole expression is negative, guess what? We can take that negative sign out. I shouldn't say out, but we can counterbalance. I should have said the opposite. We want that negative sign to be in here. We need to counterbalance it by putting a negative in both spots, right? 2 negatives when you multiply become a positive. Okay, so I kind of got ahead of myself. You want to think about the fact that that negative would turn the whole thing negative. So in order to keep it, in the context that we wanted, where it was nice and positive to begin with, we would need an extra negative sign here. Okay, so I know this is probably a little bit tricky to follow along if you're just looking at a blank screen right now. So just to reiterate, all we did was say, well, that 3, we don't need that. So let's put it on the outside of the integral because we did not actually do anything other than move it. There's no reason to counterbalance that those are the exact same locations. So I bet it's the exact same meaning no matter where the location is. We needed this to be a negative sign x, so we put a negative here. To balance that out, we had to put a negative there so that 2 negatives turned positive, which is what we originally started with. And so now we're in great shape. So we have a negative 3 out in front, and then we have a u squared, and I haven't written it yet, but the negative sign x dx, that's just du. Right, so finally, the antiderivative of u squared is raise the exponent by 1, multiplied by its reciprocal, and we still have the plus c since we don't have the limits of integration here. And then the rest of this, of course, works out pretty nicely. The 3's do end up canceling out. We still have that negative sign, and then u was cosine. So cosine x cubed would be the same thing as cosine cubed x, and we still, again, have the plus c. Right, so if you want to double check using the chain rule here, when you took the derivative, you'd multiply by the exponent. So I did a negative 3 here, decrease the exponent by 1. So that gives me a negative, a negative 3 cosine squared of x. So we have a 3 cosine squared of x so far. We get the negative sign from taking the derivative cosine. The derivative cosine is negative sine. And so again, I didn't want to write it all out, but hopefully kind of working backwards, you can see how that ended up working out just fine. And so it's a very similar setup, but it's a little bit trickier in making sure that we pick the inner function. But just be careful. Pay attention to where your exponent is, whether it's on the trig function or within the expression that we're taking the trig function on. And so the last 2 examples that I have for you here are both just making sure that we can make a good decision about what our value of u should be. Okay, so this next one, we'll say we're going from 0 to pi over 4, so back to a definite integral. And this time, let's work with sine x, cosine x. Okay, so definitely a weird one, because unlike everything else that we've done here, there's absolutely no inner function. Right? This is multiplication between the 2. I don't want to just sit down and say, well, let's make u is equal to x, because nothing would change other than we'd be working with u's in our problem instead of x's. Okay, so in a situation like this, where there's no obvious function for u, in general, just pick one. Or if you're good with mental work, you can think through again and remember that we're about to take the derivative of u. So, if you can kind of think through which one would be easier that way, go ahead and do it. But we're going to do the same problem twice, just to show that it doesn't matter. So I shouldn't say it doesn't always matter, but in this case, it doesn't matter. So let's say that the first go around, we said that u is equal to sine of x. And if I take it that route, when I use derivatives to find the differential, the derivative of sine x is cosine x. And hopefully that's the one that you were initially thinking of as the right one to do. And if you thought ahead, you'd say, well, if I made that u, I'd have to take the derivative sine of x. The derivative sine of x is cosine of x. That's exactly how I need this to be set up. And so that would be the best way of working through this. Now keep in mind we have a definite integral. So this time around, we need to evaluate our 2 limits of integration. So if I take x equals 0 and plug it into our substitution with u, you get u of 0 would be sine of 0, and sine of 0 is just 0. U of pi over 4, of course, would be sine of pi over 4. And this is one that you should have memorized. The sine of pi over 4 is square root of 2 divided by 2. So what we're left with, if I take it this route, is that our limit of integration goes from 0 to square root of 2 over 2. Sine got replaced with u. Cosine dx here got replaced with du. And this antiderivative is about as easy as it gets. The antiderivative of you increase the exponent by 1, multiply by its reciprocal, and we have to evaluate that at 0 and square root of 2 over 2. And I'm going to make this go down a little bit since I'm not going to be able to go over here. And then when you actually evaluate this, then you're going to get 1/2 times u squared, so square root of 2 over 2 squared. And then I'm not even going to write it because 0 squared is just 0. So I'm not going to write the whole expression, but you would just get a 0 here. And then finally, when you square a fraction, you square both the numerator and the denominator. The square and the square root would cancel out. The denominator squared, 2 squared, is going to give you a 4. And then lots of different ways to handle the final step here. Either reduce the 2/4 and multiply straight across, or recognize that the 2's cancel. Either way, you end up with 1/4. Okay, so if anybody's curious, there's a 1/4 of a square unit of area between the graph of sine x, cosine x, and the x-axis when you're working between 0 and pi over 4. Okay, so let's just do a compare contrast. Okay, so if I try to do the opposite and say that u is equal to cosine of x, then when I take derivatives to get the differentials, I end up with du is equal to negative sine of x dx. And this one's just a little bit harder to work with because there's that stupid negative sign here, but we know how to handle that. If we need there to be a negative sign in front of the sign, we can counterbalance that by putting a negative sign in front of our antiderivative as well, or our definite integral. And then go through, do the same thing we just got done doing. If I evaluate this version of u at 0, cosine of 0 is 1, so be very careful with that. That's an easy mistake to make writing a 0 again. And you evaluate it at pi over 4. Well, cosine of pi over 4 is also square root of 2 over 2. And so at first glance, this looks like this is not going to work out nearly the same because we have 2 different limits of integration than what we had here. Okay, but just trust the process, it's going to work just fine. So we ended up with a negative sign in front. So we have negative from 1 to square root of 2 over 2 of, excuse me, here, just remember that cosine of x got replaced with u, sine of x dx is now du, so it's the exact same u du here. Okay, and so now, just finish it out, it's going to be the same antiderivative, so we're still looking at negative 1/2 u squared that we're evaluating at square root of 2 over 2 and 1. Okay. And then, excuse me, finally here, just go ahead and do it. So this is a little bit tricky because we have a negative sign here, but we're going to have a negative 1/2 square root of 2 over 2 squared. That's still on the board, just barely. And then we're subtracting another negative 1/2 times 1 squared. Okay. So the key thing to be careful with here, especially when you have a negative in your antiderivative, is when you go to subtract using our fundamental theorem of calculus, the 2 negatives become a plus here, obviously. Okay, so what we're left with here is, we talked through this before, this becomes 2/4 when you square it. The 2's cancel out, you're going to get 1/4, but because of the negative sign, we're going to get a negative 1/4. And then over here, 2 negatives become positive. 1 squared is 1, 1 times 1/2 is 1/2. And then finally, negative 1/4 plus 1/2 is 1/4. Okay, so the real point of this example wasn't to say that there's a certain way that you should have done this that made it a little bit easier. It's just to say to try something. If it works, it's going to be the right answer. If it doesn't work, you're going to know at this step right here. If it doesn't work, you're going to know right here, and then you'll say, oh, that doesn't line up. Let me try a different function for you. Okay, so you can take a look at this. There's slightly different calculations throughout, but of course you get the exact same answer. Okay, so again, just kind of trust that the substitution method will lead you to the correct answer as long as you're making your substitution work out correctly I shouldn't say work out correctly, but you had the substitution that you need in that original expression. And so let's take a look at one more example where it's not quite clear what your value of u should be. So this go around, let's go back to a normal antiderivative. Let's say we're working with e to the x minus e to the negative x over e to the x plus e to the negative x. Okay. And so, as before, we kind of have two choices here, neither one of which, we have any hints for, right? There's nothing inside the set of parentheses. Again, we don't want to go through and just replace an x with a u or a negative x with a u because that's just going to change signs or nothing at all. So we need to choose either the numerator to be our inner function or our denominator. And so this is just literally a guess. All right, so to avoid any sort of consternation on your part, I'm going to tell you right now I'm guessing wrong on purpose. Okay, but let's take a look at what happens if you guess wrong. Okay, so let's say I'm guessing that I should choose the numerator to be my inner function. Then u would be e to the x minus e to the negative x. I find du by taking the derivative. The derivative e is itself. And the other one, it's also itself, but because of the chain rule, we also have to multiply by the derivative of negative x, which is -1, and the two negatives are going to turn positive when you do that. You still have the dx. All right, so I hope that was something you could follow along with. Just the chain rule, when I multiply by the derivative of the negative x, it's going to end up changing the negative to a positive here. Right? And at first glance, it looks like everything's golden. It looks like we have, well, there's our u, here's our du, but there's a huge, huge problem here. Okay, so when we saw something similar to this before with our square root example, when we work with the denominator, we worked with that denominator because we had a denominator in our du statement here. Okay, so just to be clear here, if you wanted to rewrite this as multiplication, you would have to write this. I'm not even doing any of the substitution. You would just rewrite it as the numerator, e to the x minus e to the negative x, times the reciprocal of the denominator. It would look like this. Okay. And in particular, that dx is not in the denominator with the rest of the expression. If you were going to put it anywhere, it's not really number, but you can kind of think about it that way, remembering that dx kind of sort of represents the width of a rectangle in that sort of context. So if you were going to think about it in that terms, it would be dx over 1. That would throw the dx up here in the numerator if you wanted to look at it that way. And these guys absolutely do not match up. Okay, so this is where you would have to stop. Right, so you just have to be careful. I kind of chose a tricky example on purpose so that we could talk through one where everything looks like it's matching up, but there is no way that you can make that equal to that e to the x plus e to the negative x dx. Maybe I should have put a parenthesis here as well to make sure it's clear how that was going. Those two things are not equal. That means our substitution fell apart here. And we can't fix this by just putting a constant somewhere. We have the whole fraction flipped upside down. I can't flip a fraction upside down without changing the whole problem. Okay, so that's what happens, or similar things. And it doesn't always have to work out perfectly like this. Maybe it wouldn't even come close to matching up. Maybe it matches up like this, but it's in the wrong position. But that's what happens if you guess wrong. So it's not a big deal. You just try to do it. If it doesn't work, just say, darn my bad luck for guessing the wrong one, and just go with the other one. Okay, so we're choose u to be e to the x plus e to the negative x from the denominator. Taking the derivative, we're basically going to get the exact same thing as before. The e to the x stays, but because of the negative sign up in the exponent, when I take the derivative, I'm going to get a negative sign in front of the e to the x, and that whole expression is being taken times dx. All right. So, comparing and contrasting here, this time, if you wanted to rewrite this as a single fraction instead of separating the dx would go up here in the numerator, right? We kind of multiply across, we end up with a dx up there, and just erase it so it doesn't look weird. And we have exactly what we need. The e to the x minus e to the negative x dx matches up here exactly. Okay, so just a quick tip. This is not quite universal. There's certainly reasons for this not to work. But if you don't have any other indication in your function about what you should choose for your inner function other than a fraction bar, in general, the correct choice is the denominator. Because when you take derivatives, it's fairly uncommon to take a derivative and then end up with something that's in the denominator after you take the derivative. It's much more common. You know, whether you're talking about polynomials or exponentials or trig functions, when you take derivatives, they usually stay as a polynomial trig function. They don't usually end up having those fractions. So going forward, maybe make the denominator your first choice. And if it doesn't work out, like I said, it's not a hard fast rule. Just choose the numerator to be u. Okay. But now we're good, right? Because this is just u, and this up here is du. So we don't have any limits of integration to worry about. So we're taking the antiderivative of du divided by u, which we would normally, at least I would normally write that as the antiderivative of 1 over u du. And so all I'm doing is separating this, just like we kind of put the dx together up here before. We can separate it out just by using fraction rules again. We just pull that out. If you thought about that as over 1, we didn't change anything. We just wrote it as 2 different fractions. Okay. Then the antiderivative of 1 over u is again a little bit tricky. Be careful with it. I'm going to do it wrong again on purpose here. But if you try to rewrite this as u to the negative first power, and then went through and said, well, I need to raise the exponent by 1 and multiply by the reciprocal, it breaks, right? This is the one that you cannot use the power rule on. So not a huge deal. I just know that it's a common mistake and it has been shown recently, so I threw it in here. So this right here, you can even draw a little frowny face on it if you want. That guy is causing a problem. You cannot take the antiderivative because you cannot divide by 0. Let me take that back. You cannot take the antiderivative using the power rule because you can't divide by 0. But hopefully a bunch of you are just shaking your head saying, well, that was stupid. I remember this one. This is the one situation where I'm not using the power rule. The antiderivative of 1 over u just gives me natural log. Okay, so a reminder, it's technically the natural log of the absolute value of u. And we're working with just a straight antiderivative, so we have the plus c here. But again, the absolute value is important because it broadens the amount of information we have. If I just put natural log of u, I could not put any negative value in for u. Here, because of the absolute value, turning it positive, I could put in anything I want for u except for 0. And so you're kind of working with twice as many numbers if you have that absolute value. And then finally, don't forget when we're not working with the definite integral and we're not evaluating, you do have to do your back substitution and plug those exponentials back in. So we're looking at the natural log of the absolute value of e to the x plus e to the negative x plus c. Okay. And because that absolute value gets in the way, there's no way to try to break this out using any sort of logarithm rules. For that matter, there is no logarithm rule for adding or subtracting. That is just the answer that you get. All right, so I think this is probably where we should stop here. I don't feel the need at the moment to go through and try to make a list of descriptions of what we did with each step. This was, I think, 7 examples now that will help you guide through the problems that you run into in section 5.5. But as always, if you have any concerns, drop me an email and I'll do my best to help.